Welcome to this explainer. Look, we all know primary fermentation does the heavy lifting, right? But maturation, that's the phase that dictates whether your beer is just passable or absolutely flawless. Today, we're diving deep into this technically demanding stage, tracking those intricate physical and chemical shifts that happen right between the end of primary fermentation and final filtration. This is where the rough edges get completely smoothed out. It's where you lock in colloidal clarity and stabilize that final flavor profile. Honestly, it's this perfect, beautiful convergence of biochemistry, physical chemistry, and process engineering.
So here's our roadmap for today. We're going to breeze through warm maturation biochemistry, take a hard look at maturation tank engineering and cold storage physics, and then dig into the exact chemistry of haze and colloidal stabilization agents.
All right, let's start with the baseline environments for maturation. The main split between traditional systems really just comes down to temperature and timeline. Ales are conditioned through warm storage, usually held at 12 to 18 degrees Celsius for a quick 1 to 4 days. And in that warm environment, residual sugars are metabolized incredibly fast. Lagers, on the flip side, undergo a much slower cold lagering process at 3 to 6 degrees Celsius, stretching out over weeks. And that extended timeline, it's highly dependent on exactly how much yeast is still in suspension and how much fermentable sugar is left in that young beer.
Now, why do we care so much about this early maturation phase? Well, at the end of primary fermentation, we're stuck with what we call green beer. It is absolutely loaded with unpleasant flavor compounds driven by yeast metabolism. We're hunting down three main culprits here. First, acetaldehyde, which gives off a harsh green apple note. Then sulfur compounds, which, let's be honest, smell like bad eggs. And finally, vicinal diketones, primarily diacetyl, which leaves a slick, rancid butter or butterscotch flavor. The whole goal here is that the remaining yeast actually reduces these green flavors. It converts diacetyl into acetone and 2,3-butadiol. And that's a massive win, because those reduced compounds have much higher taste thresholds, meaning they effectively disappear from the finished beer's flavor profile. The engineering that actually makes this happen is pretty slick. Think about a vertical maturation tank equipped with sidewall and cone cooling jackets. In a unitank system, you're fermenting and maturing the beer in the exact same vessel. Because each tank is individually cooled and wrapped in heavy lagging for insulation, the brewer has ultimate control. You can raise the temp slightly for a diacetyl rest at the end of fermentation, and then gradually crash the beer down in place without ever transferring or stressing the liquid.
Let's contrast those jacketed unitanks with a totally different approach. Unlagged vertical or horizontal tanks that are simply sitting in a massive refrigerated cold room. The crucial engineering reality here is that you absolutely cannot rely on the ambient air of a cold room to pull the beer's temperature down efficiently. It just won't work. For this system to succeed, the beer has to be aggressively chilled via a heat exchanger during the transfer, hitting exactly -1 degree Celsius the second it enters the tank. So once we cross over into true cold storage, holding the beer right around 0 to -2 degrees Celsius, the entire paradigm shifts. At these temperatures, yeast activity basically hits a brick wall, though some lager strains might stubbornly grow at a microscopic pace. But the main changes happening in the tank are no longer biochemical flavor reductions. They're entirely physical. This phase is all about the physical settling of suspended solids. We want yeast and proteins dropping entirely out of solution so we can finally achieve that brilliant, bright beer.
And that brings us straight to the physics of clarification, which is entirely governed by Stokes' law. Process engineers can literally mathematically manipulate a specific set of variables to speed up sedimentation. You want a faster drop? You can increase the particle diameter or density, increase the gravitational force, decrease the liquid's viscosity, or just decrease the distance those particles have to settle. That last one is exactly why horizontal tanks can be so incredibly effective. But practically, out on the brewery floor, we can't decrease viscosity because that means warming the beer up, which just redissolves the haze we're trying to drop out. So engineers focus heavily on two things: ramping up gravitational force using centrifuges, or dramatically increasing particle diameter by dosing finings to clump everything together.
Speaking of stuff dropping out, let's talk about what we're actually fighting when we crash the temperature. When young beer is chilled to 0 degrees, it almost always throws a haze. This is chill haze. Mechanistically, it's a reversible association of malt-derived proteins and polyphenols. They simply lose their solubility at low temperatures and bind together. The key thing to remember is that these bonds are incredibly fragile. If you let that beer warm back up, those bonds break instantly and the haze just vanishes into thin air.
But what happens if you don't control the environment? Well, that chill haze builds into a much bigger headache: permanent haze. If your beer goes through a roller coaster of alternating chilling and warming periods, which happens all the time in transport and warehousing, that reversible chill haze stops being reversible. Toss in some dissolved oxygen and trace heavy metals like iron or copper, and those proteins and polyphenols forge highly reactive, extremely durable covalent linkages. Once those form, game over. The haze is permanent. That beer is going to stay cloudy even if it's sitting at 20 degrees Celsius.
So how do we stop this before it starts? Smart brewers know that stabilization actually happens way upstream, long before the maturation tank. You've got several process interventions to cut down haze precursors. You can switch to low-nitrogen malts or nitrogen-free adjuncts to slash the overall protein load. You can dial in your calcium ions in the mash to precipitate oxalates early on. Or, in a really innovative move, you can brew with proanthocyanidin-free malt. That's a specialized malt specifically bred to completely lack the most reactive polyphenols that drive haze formation in the first place.
But if we are relying on the maturation tank for clarity, we go right back to Stokes' law and manipulating particle diameter using finings. The two big players here are auxiliary finings, usually acidified silicates, and isinglass finings. And isinglass is wild. It's actually processed from the swim bladders of specific tropical fish. It's loaded with collagen and essentially acts like an electrostatic net. It yanks yeast cells together until they form these massive, heavy clumps. By artificially inflating the particle diameter, the yeast plummets out of suspension at an incredibly accelerated rate.
Now, for true deep colloidal stabilization, we have a highly precise chemical toolkit. We're not just dropping out yeast here. We are actively stripping out the problematic proteins and polyphenols. Silica hydrogels act as adsorbents, literally trapping specific molecular weight proteins right inside their pores. Then there's PVPP, a synthetic nylon derivative that aggressively binds and yanks out polyphenols. We even use papaya, a proteolytic enzyme derived from papayas, to physically chop up proteins so they can't form haze structures. And let's not forget tannic acid, which precipitates proteins directly in the maturation tank. The science here is exact. Each agent requires strict, specific dosing rates and precise timing to do its job without stripping the beer's soul. I want to focus on PVPP for just a second, because there's a huge economic and engineering factor at play. PVPP is ruthlessly effective. When you use it alongside silica gel, you can produce beer that stays perfectly haze stable for up to 18 months. The catch? It is incredibly expensive. So large-scale facilities don't just use it and dump it. Instead, they dose the PVPP slurry inline, catch it on a dedicated recovery filter, and then chemically regenerate it. They blast it with a 1 to 2% hot caustic solution at 80 degrees Celsius, neutralize it, and reuse it. It's brilliant engineering that balances total shelf stability with the very real economics of brewing.
We've covered a ton of ground today, right? From the vital biochemistry of flavor reduction to harnessing Stokes' law and the literal molecular chemistry of preventing haze. I want to leave you with a question to bring back to your own operations. Take a hard look at your facility's process. How long is your cold storage actually lasting? Are your transfer temperatures genuinely hitting that critical -1 degree Celsius? And, based on the rigorous science we just walked through, what specific agents are you utilizing to guarantee the colloidal stability of your final package? Are you just crossing your fingers and relying on time, or are you actively engineering your stability? Thanks for joining me for this explainer. I really hope it gave you a sharper, more technical lens on the fascinating science of maturation.